Ja, die loopt.
Okay. So thanks very much. I hope you had a great break. I'm still too much influenced by it. I had the best break ever. All right, let's continue now with the there's more applications that we're going to look at. Um, Talking about bruises, we've seen all the processing, all the pre-processing, all the possibilities that we have for measuring absorption, fluorescence, applying pre-processing algorithms, applying decomposition processes. And here are some examples where we have actually turned them into real applications. And a project like this really requires the input of the physicist working on the algorithms, working on the light transport, like the engineer, working on the cameras, on the applicability of the whole thing, working with the physician, working on the tissue composition and the elements in there, working on the forensics people that can determine what is important and what's the requirements for them. So there are a lot of people involved in such a project. And Richelle Hoveling and Barbara Stam were PhD students on this particular one. So they have basically done the work. But as I told you, we can do scanning of blood in the visible part. We can do scanning of water in the near infrared. We can do temperature measurement in the far infrared. So it depends on the target of interest and the host material to what gives you the best contrast and how you can measure these things best. So the target of interest here is blood and the bilirubin in this case, maybe also some methemoglobin, maybe also some other forms of hemoglobin, for instance, carboxyhemoglobin or some other forms. But they all have very specific absorption profiles in the visible part of the spectrum, which is very good because it's cheap. Cameras in the visible part, and it's easy to work with. You don't have UV radiation, you don't have very expensive near infrared spectrographs. And the host material is usually skin. So that's surrounded, our target material is surrounded by melanin, fat, and water. And this is basically how we physicists look at skin, as some stuff, some pea soup, a lot of stuff in there, and we want to find this one particular component which has slightly different optical properties. So the skin, melanin, fat, water, we have to separate our target of interest from these components. And this is the application. So child abuse is well, it's commonly occurring a lot. These are some old numbers. It's increasing, but also because the incidence is really increasing, but also that we are more aware of it. It's more common to report it, and it's estimated like half or 2/3 of the kids that are abused. We cannot make a very strong suspicion, too strong or strong enough to do an intervention. So there are absolutely no good indicators of child abuse. Child can be scared. It's a character. It can have a very unconvincing explanation for certain wounds, or maybe the wounds are inconsistent with developmental skills. So the preferred, as you called it, locations of bruises are different in different stages of development. When you just start to walk, you have bruises on different sides of the body. And then when you're just crawling, or when you're not able to roll around, it's all depending on the development of the kid. And one of the things is the color of the bruise, but that's, of course, there's no good model as of yet to get a good age estimation. So what we have now is only a niet-pluisgevoel. And there is something wrong gevoel, but the official word, and because medicine is all in Dutch, of course, it is a niet-pluisgevoel. So there's a whole team looking at the behavior of the kids, the situation at home, but also radiology images if available, behavior of the kid towards the parents. Usually there's a long time between the accident and when this child is presented to some professional. And that all adds up to a niet-pluisgevoel, something wrong feeling. I don't know if that's correct translation, but there's nothing quantitative to it. There's no diagnosis. There's only a very strong feeling of something's wrong here. And then you start to question and further investigate, but there's nothing quantifiable except for maybe like how far these bruises have progressed. And if you can calculate it back to T is 0, then you may have something. And that's what we started with in 2007 or something. So a long time ago already, 13 years old, that project, a couple of PhD students. But this is the rationale here. If you're looking at the literature, this is the like the estimated age. These are the different literature sources. There's yellow, green, yellow, 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 yellow. We look at the yellow now a bit, and it's goes from 1 week to 2 weeks to nothing at all. So there's no good indication like this. You cannot get the age right. Looking at the color makes sense because we are physicists and we know why. Sky is blue, things are green. Can have all the colors depending on depth and optical properties of the skin, of course. Here's some examples. Here you can see the bluish, reddish, or the bluish, yellowish bilirubin, and this is the hemoglobin in the skin. Here, this turns really a bit blue here, so it's a bit deeper, and this is the blue spot that you have. So we were developing this method, doing spectral imaging, but also with a mathematical simulation model. And first, we had to understand the healing processes in a bruise, which seems to be super straightforward because we know what bruises are and we have them, well, always. But still, it's not of interest to a physician to understand how bruises heal. It's just of interest how they get there. And if they're more than usual, or if they're in unusual places, why do you have a bruise? Not so much how it heals. So nobody could give me an answer on the exact processes of that, the healing mechanisms. So we had to find that out. And then we did a lot of measurements doing spectroscopy and spectral imaging on the bruises to find the predictable processes that we could use to say something about the time. And we did that by performing spectral measurements and by designing basically a finite difference model, a finite element model with elements of the same size. So it's a finite difference model. I'll explain you more about that. And there's another expertise required to develop this spectral element finite element model. So after many measurements, more than 500 measurements on students, on victims of crimes at the community health service, more than 500 bruises there. But also we had an easy bruiser here as a student. We could just tap him on the shoulder and then somewhere in the afternoon he would get a bruise, and we could do a lot of measurements on that person. But also volunteers here, and I'll show you how we made these very well-controlled bruises. We did a lot of measurements on that to see if there were any controlled or any processes that we would see each time that we could use then to build an aging model on. So we found that the areas with elevated concentration, so the area with elevated blood content and with bilirubin, they change predictably. So the ratio of these two areas, they have a kind of course that was very predictable and that we could use to determine the aging on. Not so much the amount of bilirubin or hemoglobin that was varying too much in the different areas of the bruise, but the size of the areas itself turned out to be very predictive. So what we have here, there's an impact, there's a blood pool, there's free hemoglobin going into the skin, there's hemoglobin diffusion, and some of it is converted to bilirubin. So you have something like this with the core of hemoglobin slowly diffusing outward, and then there's bilirubin going faster, and that's these differences in sizes of area. This is what we measured with spectral imaging. And then at some point there's clearance, and then it's fully converted, and the bruise is healed again. So this is basically what happens in the skin. And we did our physicist best to make a model of that. So we have like a couple of layers, I'll come back to that, to simulate these areas. So there's an impact first. Oh, whoa. I'm missing all the animations, I think. Oh, well, there are no animations anymore. So what we can see then is after some day, there's an area of hemoglobin which slightly goes down because it's converted to bilirubin. And here there's production of bilirubin and diffusion of bilirubin. So the area is expanding until things are converted. So these are typical curves for a bruise. And we could see these curves like this a lot. So we were thinking, if we now develop a mathematical model, and we physicists do it like this, there's a layer that we cannot see, subcutaneous layer. There's a bottom layer here in the dermis that we do not see, and there's a top layer in the dermis that we do see. So if we just put a blood pool down there, and we have a conversion, Michaelis-Menten enzyme kinetics to bilirubin. So the hemoglobin here is slowly converted. And we have diffusion of hemoglobin in the skin outwards, so to the different cells in the finite difference model. These are the motors that drive the diffusion. So there's active diffusion because there's blood pressure pushing the blood in the skin, making it diffuse. And there's passive diffusion because there's a high concentration of blood at some location and a low concentration here. So that's passive diffusion. So you can describe the development of the bruise in the diffusion laws, Darcy's law, Fick's law, and the conversion law of Michaelis-Menten kinetics. And it was a kind of a desperate way to solve this problem because it turned out to be very difficult to predict how a bruise would heal. But at the end, it turned out to be very successful. So here we put a blood pool down there in the model. And after some time, we can see it appear in the top layer with a little bit of bilirubin around it. And then you can see the bilirubin expanding, diffusing, and while the hemoglobin is being converted. So we can now simulate a bruise. The blood pool we measure in a patient or in a victim, we put in here, and then we calculate how a bruise would develop over time. So this is the measurement of a bruise here again with the bilirubin and the hemoglobin. And we just continually, do an iterative loop. So we have initial parameters, and we then do a simulation of the bruise, and it's usually totally off compared to the measurements that we do on the patient. And then we just adjust the parameters until our model matches the measurements. And then we know we have them right. Then we can calculate it back to T0. So here we started about 20 hours after inflicting of the bruise, and then we did a lot of measurements. So this is not super realistic, but this is the finite element model. So we measure the areas on the patient. We do like an initial guess of the physiological parameters, like the diffusion speed and the activity of the enzymes for converting blood into bilirubin. We do a simulation. If they do not match, we adjust the parameters. So we do a loop until our measurements match the simulations, or the other way around. And if they match, we know that the model accurately describes the development of the bruise in that particular person on that particular body part, and then we can calculate it back to T0. And that way we can just work on every patient on every location. And this is the way we produce these bruises. This is a weight of about 400 grams. You can see it on the skin of a volunteer. And here you can see the actual mechanisms of how a bruise is created. There's a shock wave going through the skin. And this is 450 grams from 1 meter high with a kind of nice tip on it. And here you can see the progression of this shock wave through the material, through our skin. And it is not so much the point of impact which creates the bruise, but the ring around it that creates, that's where the skin is expanded most. So that will tear the vessels there. So if you have, for instance, a squash ball, same thing, or a tennis ball or a hockey ball, I know what kind of people you are, but if you're hit by a ball like that, you will usually create a ring of blood around it. And that's not the location of impact here, but it is the shock wave. This will bounce up and down a couple of times. So that's why it's going back. This is super fast or super slow down. So it really is a kind of painful experiment, but we used it on the lower arm, the inside of the lower arm, to create kind of reproducible bruises. Here again, you can see it go down. And this first part is not so much of a problem, but here, this is where the shock wave is moving through the skin, tearing up the vessels, and that's creating that red ring-shaped bruise here. And then it bounces up and down a couple of times to it goes up and down and up and down. Well, here I stopped. Yeah. So this is the way we created these bruises and measured a lot of times. Here's an example. This is the measurements that we do a couple of times on a certain bruise, then we compare that with the calculations that we can do, and then we can come up with a time of impact. So we can calculate the time at which a bruise was caused. And for a well, a lot of measurements, we can go down to sub-hour resolution time, but usually when in longer, more bruises, the time is much longer. So we understand now how bruises develop. By using the model and spectral imaging, spectroscopy, we can assess these physiological parameters. We have to measure multiple times in order to compare these measurements with our models to see if we can get the kinetics right. And the method is now validated at the Emma Children's Hospital and at some volunteer study somewhere among teenagers. They're doing that now. They're doing the measurements, and they're having sporting incidents and stuff, and they give us the data that we can work on to validate our model. And we have a small extension. Usually when a body is found dead, after a certain time, the blood sacks down and settles at the lowest part of the body. So this particular body was turned to its side. But we want to use spectral imaging and the analysis of the different components to see if there were any bruises here, which is very hard to see. It's the same technique, same analysis, everything. But here it's the host tissue is not so much the normal tissue, but here it is a very well blood-filled tissue, and in that tissue you will have your bruise. And then we can measure if it was caused before or after death. So here are some accuracies of this model. 9-hour accuracies where we started measuring at 5 days after causing the bruise, and some other measurements. So we're working on that method right now for the kids before we applying it to the to abused kids, of course, because the things that we're saying is very sensitive. So these are the bruise measurements. One very nice application going from spectral imaging to spectral imaging plus finite element modeling to a application in practice, and more on the crime scene. Very well comparable is the measuring the age of blood stains. Blood is of course encountered a lot on the crime scene. And here we're not looking at conversion of hemoglobin to bilirubin, but here the blood is converted into methemoglobin, the oxidation, and denaturation to hemichrome. And these optical properties differ, as I already said. So you can already see a color change, and this was also the way. We thought of this method basically. You were sitting looking at a stain and I thought by myself, is this a bruise? Is this a blood stain or not? Because it was brownish and it was in a kind of public place. So I thought, oh, this is dirty if it's blood, but I cannot see if it's really blood. So I thought, how would they do that on crime scenes? And it turned out there were only chemical methods. So then we thought, hey, this may be good for an optical method. And then we started to do the blood stain measurements. And there was at that time no method to measure the time of deposition, which is super important in forensics, because if people find blood on the crime scene, you can get the DNA, then you nail down the person. So that is whose blood it is. It's easy to determine. How did it get there? Well, you can usually use these kind of blood spatter patterns. You can distinguish between an arterial bleeding, or you can see if it was an active stain, a high impact stain, or a low impact stain, if it was anything, how much times people were hitting that particular person based on the blood spatter patterns. But when, that's a problem. Now, a lot of times when we see blood at crime scenes, the suspects say, of course it's my blood, because I had a relation with this victim like 2 or 3 weeks ago. And I was shaving and blood was going everywhere, or I walked again with my head against the wall. Of course there's blood here and everywhere. Totally makes sense. So that's a problem, because then we have to prove that the blood was really related to that incident, to the crime. But there was absolutely no method to determine the age of blood. Now, if you're looking as a physicist, here we come in play again. So cherish your toolbox and your knowledge, because you can do a lot of things in the forensic field still. It's super unexplored for physicists. But a very simple thing that we would immediately think of here is spectroscopy. The color changes over time. We know that. When it comes out of the body, there's pure oxyhemoglobin, very bright and red. And when it ages, it becomes just darker red. So it totally makes sense to use spectroscopy. So did we try that, of course, and the first measurement was like this. When we corrected for the intensity, we could see here, and this is reflectance, so high absorption, low reflectance here. Here the absorption peaks of oxyhemoglobin, and here again, as I showed you before, the peak of methemoglobin, going from 1 minute to 1 week. And this basically changes as the arm of a clock. So how easy can you get it? But there was no method available in the forensic field, despite the high forensic value. So that's crazy. So this was a very logical thing for us to do. The real reaction, the chemical reaction is much more complex, but we're only interested, simplify things as much as possible, only look at the relevant components for us, and then you can make a nice model. So here the blood stain is 1 hour, reflectance, so the opposite of absorption, after 1 hour, 1 day, 7 days, 56 days. Hey, still things are changing. That means that you can calculate the time of deposition back as long as, like in this case, 56 days, because there are still changes. And that's cool. That's something that, well, nobody was thinking about. And it's just purely by translating the things that we were already doing in medicine into this medical forensic application. So we were doing this for like years and years and years, and we were able to develop these algorithms. You've seen before, like the Kubelka-Munk stuff. Hey, food. We were using those algorithms to calculate very carefully what the absorption properties were, but we were already seeing here that we could nicely distinguish young from old stains. And this is very important new information about temporal aspects of a crime. We can put things on the timeline in order to get some idea of when things happened. We were comparing bloodstains in an apartment, in a house, to the bloodstains on a victim, on the crime victim. We were comparing bloodstain ages of bloodstains on the suspect clothes to the bloodstains in the crime scene. We were comparing bloodstains in different rooms to see if these would match, if the story was true. And this is directly related to all the stuff that I told you about before, like the bruises, like the oncology, just spectral imaging. So this is all very nice to keep that in mind. And in practice, it's, like I said, very simple. I can play this movie, but I want to say a little bit more about the fluorescence as well in the 20 minutes that I've left. So here we're doing, well, recordings of spectral cubes.
Remove the lens.
And I'm rattling on, so that's not so interesting. But here we're looking at things on a black t-shirt, or we can look at things on this dress here, which is super complex to inspect. There's no bloodstains that you can see. And in this particular example, we were examining bloodstains on t-shirts to see if we could determine the age of that. And it's very simple to use. Just push the button and you have your spectral cube. The analysis is a bit harder.
Scene with a little drip.
Sorry. So we've made it, that's also a nice thing to work with the experts. What do they want to see and how easy must an end user have a front end of a program? So here you have the black t-shirts that I just imaged. And here is the bar that you can select your wavelength with. You can walk through the spectral cube and you can see the black. This is the visible part still. That's like blue-greenish. Here we go to the red, still nothing. But if you move up the bar higher, the color of the cloth disappears, and there is your trace. The same way with wounds on skin, those kind of things we can nicely inspect. So you can see you can do all kinds of tricks with this. And also with a more complex thing like that dress that we have here, it's very hard to inspect. And even if you look at the different wavelengths that we have here, because there are some beers, bottles. So here you can do more with a spectral cube. You can select a stack of images and you can create contrasts. So with the bandpass filters and the long pass filters, we can all do that afterwards. You don't have to put these filters on your camera. We can work, and here you can see we have kind of eliminated now all the patterns in the dress by going to a very specific small wavelength band And here are your forensic traces, all your blood stains and everything in there, which is not possible with any other technique. So this is also of huge forensic value. Now, if you go to the bloodstain measurements, we can just click on these blood stains, and then we obtain their spectrum. Yeah, we can do ratio imaging. So divide two images, and then all the wrinkles disappear. Will be great application in practice with in imaging. It's possible, and then you have a very nice view of your stains again without any interference of your patterns that you have here. So when you divide two images, you just get this very smooth image with the blood stains. And if you just take the spectra and these are automatically analyzed, well, you can see this is fake blood and these are the real blood stains, automatically calculated. And I'm calculating the hemoglobin fractions that will result in the age of each individual blood stain. So this is something that you can say, is this one event or is this multiple events? And in this case, it's one shirt, but they're older and younger blood stains here, which is not visible with the naked eye, and that we can use our technique for. So it's this is how we've made it into an application. Any questions about the more medical forensic, medical bruises, crime scene spectroscopy part? No questions. You can also always send me, of course, an email, or you can. I need physicist people to do more internships because I need your knowledge, your toolbox, and your way of thinking. So you're more than welcome to work in this challenging field. Also the child abuse and also the body stuff. That's very nice, I think, and really unexplored field of research for researchers, for scientists. So I had also this audience participation part, but I will probably not even make it this year to that. Last year it was somewhere in the middle, but now it stretches beyond these 2 hours even. So you're so lucky. Well, I don't know if you're lucky because I think you're dying to do something active now, but I will rattle on a bit. I will rattle on. Not really like what you should do in this online lecturing, but can't help it. So we've looked at absorption spectroscopy. We've looked a little bit at fluorescence, but not so much. But I will go to a fluorescence diagnostic technique, also with a spectral camera, but then for diagnosis in tissue. Whereas Professor Sterenborg will talk more about this application in the next lecture. And I hope I'm still there because you're all frozen now. About spectroscopy. If you're all frozen, I'm probably the one that's frozen. But
I can see and hear you fine. No.
Oh, that's good. You're just fixed. Okay, so I will just talk more about also the physics around this light distribution, about pharmacokinetics that we have to take into account, the detection and the data processing. So same thing as we've seen before about the reflection spectroscopic imaging. Fluorescence imaging also has a light source and a camera, but the light source is not there. We're not looking at the same wavelengths that are emitted by the light source, but we're looking at the fluorescence light that's generated by the molecules in the object that we're looking at. So now our light source is an excitation source. We're going to excite the molecules to a higher energy level. They will fall back and they will emit light, fluorescence light. There's some heat produced also in that process. It's going to a higher electronic level. It goes down a bit in the sub-levels, the more vibrational levels, and then it's going back to the ground state. So the energy that's emitted is less than that's what's coming in. So the wavelength is slightly longer. The emitted wavelength is slightly longer compared to the incoming wavelength. So we're exciting tissue, human biological materials, usually with UV light or blue light. And then what comes out of there is usually yellowish, greenish light, a longer wavelength. And the wavelength shift between the excitation and the emission, that's the Stokes shift. that varies between different components. But mainly, if we want to use fluorescence for detection, we just put shortwave length light on there with a large bandwidth. We block that excitation light with our long pass filter so that we are only looking at the generated fluorescence light, because the fluorescence light is much lower in intensity, and otherwise our eyes would be totally saturated with the blue light or the UV light that we use to excite the light. So we block it using a long pass filter. That's it. Light is generated here in the tissue and going to the detector. All our cells fluoresce, basically. Proteins, they fluoresce a lot. That's what we're using in forensics to detect body fluids. But also tumor cells, they fluoresce slightly different from other cells. There's tryptophan in proteins, which is responsible for a lot of fluorescence. There's all kinds of components in the skin. There's elastin and collagen. Also in vessel walls and in tissue, there are these molecules that fluoresce like crazy. But we can also externally apply or just a dye that accumulates selectively in the tissue that we're looking for instance, in the tumor. So we're looking at the three parts here: the excitation, the emission, and the fluorescence part. This is rotating, super nice. For excitation, we want to get, of course, enough light in the tissue to get all the excitation there. For that, we can use different types of fibers and light applicators. We can do all kinds of calculations on where, how much light we have to use for illumination, how deep the light is, and we basically, a lot of time we use Monte Carlo simulations for that, as I talked about before, and probably you've heard about it before. You just define a medium here with its respective optical properties. In this case, it's uniform, thick layer, but it can also be very layered with all its individual optical properties. And you just shoot in 1 million photons, and by probabilistic models or decisions, basically, it's basically gambling with throwing the dice. You determine your photon distribution, and it's all governed. The restrictions are in the optical properties, the scattering and the absorption, that basically determines this distribution. So it will give you, after enough photons to reduce the statistical noise, you get a distribution like this, and you know how deep you can go, and if you can see structures that you're actually looking for. If a tumor that you're looking for is actually usually at a thickness of this depth, 4 millimeters, this illumination will not be enough to see that. So you can play around with that. You can see how deep it goes. This is a vessel, excitation light distributions, different sources. You can play around with all the parameters to design your optimal system for light delivery to the tissue for either diagnostics or photodynamic therapy. So that's the first part. The second part is the photosensitizer, or the drug that you give to people in, I haven't seen rotating thingies since the invention of PowerPoint, and it was super hip, but that was in the 90s already. Sorry for that. I don't know how they still are in here. So the photosensitizer is a typical drug that has both fluorescent properties, but can also convert its energy to create a singlet oxygen. So there's oxygen, there's the photosensitizer. It gives it energy to the oxygen, which will go an energy transition into a singlet state. And with that, it becomes very active very reactive, almost like a radical. You cannot call it a radical, it's singlet oxygen, but it can destroy like the environment where it's in. So if you have a photosensitizer in a tumor and there's oxygen there, you can illuminate the photosensitizer. That will give the energy to the oxygen. The oxygen will destroy the tumor, and that's the therapy. Or the photosensitizer will generate fluorescence, and then you can see the tumor. So that's the photosensitizer. Well, we can deliver it there specifically in the tumor, because the tumor vessels are usually a lot more leaky compared to normal vessels. You can locally apply it. Well, there's a lot of demands on the photosensitizer. You also want to get it out of the body very quickly, because you're photosensitized. So it means you cannot walk in the sun, otherwise you get burned very heavily. And in the first generation photosensitizers, you had to stay inside for more than 3 weeks. Otherwise you would get outside, you will totally get burned, because of the photosensitizer still in your body. And nowadays, these are cleared much more efficiently, and these are much more localized in the body. But well, still some applications require that old photosensitizer, and the people are covered going through the hospital. Even ambient light is too much, covered under this blankets and sheets, going to the OR. Then we do the elimination. Then we have to cover them again. They have to stay inside. There's also a disease called porphyria, where the porphyrins in your skin are not cleared. And that also creates these burn wounds. So these people have to stay inside and can only go outside during the night. And we create porphyria with our photosensitizers, but then a transient one that goes away again. That's basically how we do it. But we want to do, well, this is an example where we apply aminolevulinic acid, which is naturally occurring in the body. It's part of the pathway of making hemoglobin, making heme. That's part of hemoglobin, the heme molecule. First, there's aminolevulinic acid. It's converted into protoporphyrin 9, porphyria, you see the connection. And that is converted into heme again. So we give an excess of this ALA, which is also there naturally in the body. That creates a lot of protoporphyrin. Usually there's a feedback cycle to reduce the amount of ALA, but we just give a shitload of ALA. And then there's an accumulation of protoporphyrin, because this conversion step to heme is slow. So there's an accumulation. And then the protoporphyrin is photoactive. Patients with porphyria have a lot of protoporphyrin in their skin and get burnt. Now, the tumor is much faster in this conversion compared to the normal skin. So there are concentration differences. So you can treat or you can diagnose at the moment where there's a lot of protoporphyrin in the tumor compared to the normal tissue. And that's the point that we want to look at. This is the excitation at 405 nanometers. This is the emission at 630 nanometers and 700 nanometers of this protoporphyrin. So if you want to treat, we can illuminate a tumor with 405 nanometers, or we take another excitation peak here at 512, or we can even use 630 nanometer. There's a small excitation peak here as well, to get deeper in the tissue, because short wavelengths don't go so deep. And we can do diagnosis by looking at the fluorescence emission of this molecule. Now, this is the conversion of the aminolevulinic acid into protoporphyrin. There's an enzyme kinetics involved in that, which seems to be very complex, but it's a Michaelis-Menten kinetic. It's just the reaction rates that you can work with. And this is basically what you have to look at. So the speed at which these changes occur depend on the amount of ALA that you offer to that reaction. This is the maximum rate of conversion, and this is some Michaelis-Menten constant that depends on the affinity of the enzymes to go into that reaction. So this is the Michaelis-Menten equation that we can use to calculate the conversion of ALA to protoporphyrin. So if you describe it into a series of equations, and this is what we physicists like, of course, there's ALA in the system, it's distributed. This is just the time constant here, exponential pharmacokinetics. Then the amount of ALA is increased because there's ALA going to a certain location, and it's decreased because of the conversion to protoporphyrin. And this is the rate of change by this Michaelis-Menten constant. Now, the protoporphyrin is increased because there's ALA converted, and decreased because it's broken down further, or it's converted further into heme. So this series of equations you can use to calculate when you need to change or to treat or to diagnose. And this was basically the assignment that I had for you, to use these parameters to calculate the peak. So when is the protoporphyrin maximum, looking at these Michaelis-Menten constants. And that would mean you had to do that in Excel or some other program. You probably do it in Python to create the amount of ALA at a certain time. But I only have like a couple of minutes, and those basically you're totally saturated with all my rattling on, so I will not do that. I will leave this on the video. But the answer, so you can make a kind of Excel sheet with time, Then you can first make the amount of ALA after the distribution, the ALA at the cells, so that's decreasing, increasing because of this, decreasing because of this, and then the protoporphyrin here. And after 30 minutes, you would find that you will have like a curve like this, and this would depend on the amount of ALA you would give to the patient. So you can calculate the pharmacokinetics using all these equations, and that's the role of the physicist again. You can nicely, you don't have to do all the experiments with all the different doses. And that's what we had to do before. So we now know if we give a certain dose, its maximum in the tumor and what the level in the other tissues is. And we can calculate, for instance, the tumor versus small intestines ratio. So here we can see we have an optimal contrast between the tumor and the small intestines. Then we can either diagnose or treat. Tumor liver, the other way around. So the liver has, well, a lot more here. So the tumor ratio is lower here. And then we can still get this contrast. So we cannot treat it, but we still see the contrast. The tumor is here much darker compared to the liver, if we're looking at the fluorescence. And if the tumor is in the small intestines, the tumor is much brighter here. So, and it's also a nice way to treat. So we can use the pharmacokinetics to get our treatment or diagnosis strategy. That's that part. And then the detector, well, still moving. Then you get something like this. So here, this is the white light inspection in the bladder. And here you can see the accumulation of protoporphyrin in the tumor, in the bladder, illuminated with blue light. The blue light is filtered out because of the long pass filter in front of the camera. And then you can nicely see a high contrast image of the tumor, which is otherwise quite hard to see if you have to inspect a large area. Also here, these two are very easily to see, but to really differentiate, these two are also quite okay to see, because this little satellite tumor is very hard to see if you're only working with white light inspection. If you apply ALA in the bladder, instill it, and leave it there for 4 hours, then you're going to go in with your endoscope, illuminate the tissue with white light, UV light, and look at the emitted fluorescence light. You can nicely see a full image of where this tumor is. Also satellite tumors, here's a small one, here's a small one, which is very difficult to see on the normal white light image. So this is a very nice tool for the oncology doctor, for the surgeon, who needs to assess the situation. Maybe you have to debulk it, meaning taking tumor tissue out, and decide on how to advance the treatment after this. Well, the future is, of course, nanoparticles, all kinds of new dyes, things that will go to the tissue. And before I close, these are the main research topics still in fluorescence diagnostics. Particles, nanoparticles are very nice, of course. We can use all kinds of antibodies to selectively attach these new contrast agents to the tumor. We can do all kinds of ways of administration. We have all kinds of new cameras to create contrasts. So these are the main research topics still there. Well, breast tumors also, some of the optical contrast agents, instead of using X-ray light, we can do an optical tomography and finding the tumor in that way. These things are still under development, but they will, of course, create a much easier way and a less harmful way to find these tumors, which are quite deep embedded into the tissue. So that's the nanotechnology part. I'll not go into this. I will stop because I totally saturated you. Sorry for the rattling on, not stopping for a practical assignment, which was basically my assignment of Dirk to the lecturers, to put an assignment in there so you would not be passively staring at the screen the whole time. Furthermore, I'd like to thank all the students that left their camera on, because I'm basically talking to you. It's basically talking much better than talking to only black screens. So thanks for that. And if there are any questions, I would just tell you a little bit more about the modulating cooling body. That's the thing. Bor already has some idea of that. It is super simple. It is the cooling turning on and off. You're looking with spectral imaging, because you're not going deep into the tissue. The you're only looking at a very superficial layer because you're looking at such long wavelengths, which are immediately absorbed by water. So you're not getting any information from deep into the tissue, only really the surface temperatures. And when the cooling switches on, there's a kind of very strong wind, cool wind, airco over that body. So the surface cools down a bit. Then they switch it off when the cooling went down to 4 degrees. And then there's heat transport from the core again to the skin. So then you get this, if you look at the surface, you get this modulation of the temperature. If you would look at the core temperature, that's very stable and nicely conforming to a more Newtonian cooling. But the skin surface that we're working with is really very sensitive for the surface effect. Sorry for the not so interesting explanation of this all. So if there are any questions, please tell me.
Maurice, is it an idea to have that assignment that you had in slides to use that as a short homework assignment?
Absolutely.
People are shaking their heads in disbelief.
I will isolate these 2 sheets, or they're in the sheets that I will provide to you.
Yeah.
And then it's the answer is also in there, but it's nice if you can play around with the dose and the dose-dependent kinetics that is in the tissue. So. Yeah.
And then maybe if you have like 10 minutes or 15 minutes Monday afternoon, then
it's very nice, because what it means, and that's the cool thing, like the impact, is that we had to do animal testing a lot for each individual dose to find the pharmacokinetics. Now, if we have these specific tissue-specific properties, we can make a very nice theoretical model of that, and then play around with all the doses and all the contrasts that we like, without having to do all the extra experiments. So this is a kind of a thing that may motivate you also to look a bit into the pharmacokinetics of the problems here. So that's they are in the slides that I will after this lecture give to Dirk again, and they're for you to try.
Alrighty.
Yes. Are there any other questions? I don't see anything appear in the chat. Dirk has my email, and otherwise they must be somewhere on the slides probably. Otherwise, I'll put it on the first slide, and then you can always contact me for more information. Yes? Cool. Thanks very much.
Right. Thanks. In that case, I have nothing more to add.
Oh, so yeah. Those were your last words, right?
Those were my last words. Famous last words. Nothing more to add.
Famous last words. All right. Thanks very much.
Okay. Bye, everyone.
I have to find a button to sign off. Oh, here it is.